Hi, my name is James Han, and this is my Lab 4 report on oscillations. In this experiment, we investigate the motion of spring mass system, where the mass both swings in an arc and oscillates along the spring. Our main goal was to compare theoretical predictions with real experimental data. We analyzed the motion using tracker to extract position data and model the motion computationally in ClosedScript. Throughout this lab, the key physics concepts involved were Newton's second law and the conservation of energy, including kinetic, gravitational, and elastic energy. The experiment investigated the behavior of a spring mass system in which attached mass both swings in an arc and oscillates along the spring. The object is to compare the theoretical predictions of the motion with an actual recorded movement. Equations. To model the motion accurately, we calculate all the forces acting on the mass. First, the gravitational force is given by F equals 0, negative mg, 0, which always acts downward. Next, the spring force is F equals negative k times L minus L0 times L, pulling the mass back toward the spring's relaxed length. The net force is simply the sum of those two. We then use Newton's second law to update the motion over time. The velocity changes by V equals Vi plus F net over m times delta t. And the position updates as R equals Ri plus velocity average times delta t. These updates run continuously in the simulation, letting the virtual mass move exactly as the real one, with under those same forces. Our system included a mass, a spring, and Earth's gravity. We ignored external surroundings and assumed that no outside work was done in the system. The initial parameters were initial velocity 0, meter per second, initial position negative 0.00652, negative 0.705, 0 meter. Gravity is 9.8 meter per second square. Spring constant is 6.83. The lex length is 0.7 meter. These same values were implemented in both the tracker analysis and ClosedScript simulation to ensure consistency between experiment and model. The lab has two main parts. Part 1 was the experimental analysis. We used tracker to study the provided spring mass 2D times point MP4 video. By calibrating the stick and marking the mass's position frame by frame, we extracted its x and y position over time. Part 2 was the computational modeling. We entered the measured data and initial conditions into ClosedScript, implemented our force equations, and simulated the motion. Afterward, we compared the simulated trajectory to the tracker data to see how well theory matched reality. Let's look at what we found. For the x position first time, both the experiment and simulation had the same period of oscillation, but the amplitude was slightly larger in the real data. For the y position first time, again the periods matched, yet the amplitude differs slightly in the opposite way. Overall, both motions were clearly periodic and showed expected sinusoidal patterns. When analyzing energy, the total energy stayed almost constant throughout. Whenever kinetic energy increased, potential energy decreased, and vice versa. This confirmed the conservation of energy. The small fluctuations you might see in the plots likely come from experimental noise and tracker inaccuracy. This is the computational model. This is the result. Similarities and differences. X position first time. The experimental model showed larger fluctuation compared to the predicted model. Both had the same time period of oscillation, but the amplitudes were different. Y position first time. The experimental model showed smaller fluctuation than the predicted model, like the X position. Both had the same time period but varied in amplitude. Overall energy, the total energy change stays close to zero because when one type of energy increases, another decreases. The graph isn't perfectly smooth due to the limitation of experimental data. Overall comparison, the experimental data lines appear less smooth because of slight inaccuracies in tracking the motion. The sources of errors. Center of mass. The calculated center of mass might not be accurate for each frame. Computational limitations. Model may not capture all real-world details. Assumes no external world. Work is done by the surroundings. Additional questions. For your model system, is the energy principle satisfied? Yes, the energy principle was satisfied. According to this principle, energy cannot be created or destroyed. This is shown in the energy change graph, where the total energy remains nearly constant. Any small fluctuations are likely due to measurement or data collection errors. As one form of energy increases, another decreases, maintaining a balance. This demonstrates the conservation of energy in the system. To find the period of oscillation, identify two consecutive peaks or valleys and measure the time intervals between them. Estimated period from x position was 1.5 seconds. Estimated period from y position was 1.5 seconds too. The estimated periods for both x and y position are the same. In simple harmonic motion, the period depends only on the system's mass and spring constant. Therefore, it remains constant regardless of the direction of motion. The restoring forces always act to bring the system back to equilibrium, so both the x and y directions share the same oscillation period. Thank you for watching.